Thank you for inviting me to this conference. This is a really exciting time as we see many applications of unmanned cargo moving along. What is important here on is to be able to safely accommodate these operations in the airspace system in any country and across the country. So I will be talking a little bit more about how best we can leverage and accommodate them in the national airspace system of individual countries. As you can see, that my talk is focused on airspace system, and one of the transformation drivers is the diversity and density of airspace system is going to change. Obviously, there are technology upgrades that need to happen, and we need to worry about giving access to the new entrants. But fundamentally, the diversity and density of these operations are going to change, and it will change in a much more rapid way than what's happened in the last 100 years. In the future, density and diversity of these operations are going to continue to evolve, and we need to accommodate them in a seamless fashion. Fundamental premise that I would like to propose is the airspace system has to be ready when these vehicles are ready. What we have seen in the past is that drones have been ready in terms of their technology in the conceptual basis and the market conditions and operations, but the airspace system is not ready to accommodate them. And that sort of limits our ability to accrue the value of these unmanned systems. So I am proposing that we do a concerted effort in trying to make sure that the airspace system at large is able to accommodate them so that we can continue to evolve and innovate on the unmanned systems. So here are the two things that are going to happen. On one side, these drones and unmanned systems would get smaller and smaller and will operate at the local, regional, urban, advanced air mobility level for people, goods, as well as information transfer. And then they will also get larger and operate at different levels of altitude. So you can imagine them operating below 400 feet if they're small drones. You can imagine them operating at 60,000 feet and up if they're doing basically cargo, or they are just supplying internet of all kinds. So these are different operations that we need to look and say how best I can accommodate all of these at the same time in the same airspace in a seamless fashion and without having to have them wait around. So we have high altitude operations, we have commercial space. If you leave the commercial space operations for a minute and you focus on the rest of the operations from 400 feet and below, the small ones to very large ones, we have interesting complexities of accommodating them in the airspace system. So here is a picture that I want to show you from India, and for those who have gone to India and visited, this is very familiar to you. It basically shows that the mixed equipage is a big problem, and the reason for that is the intent information is not shared widely. So the cows don't have the intent, or if they do have the intent, you don't know what that is, and the cars have the intent and they stay in their lanes. But this heterogeneity is the causes the complexity anywhere in the system, whether it's on the road, on the airspace. And I think that's the premise that I'm trying to propose, that in order to accommodate unmanned systems, we need to understand the heterogeneity that is going to be with the manned and unmanned aircraft systems and how best we can couple them together to make sure they are interoperable. Now, in the future, that mixed equipage problem will manifest in the airspace with this kind of picture, where you will have supersonic, hypersonic, you will have commercial space going up and down, balloons, you will have long endurance unmanned aircraft systems, you will have manned systems, you will have urban air mobility or advanced air mobility type electric vehicles, as well as smaller drones. So all those heterogeneous vehicles, their performance characteristics is different, but we really need to figure out how to accommodate all of them simultaneously. One of the critical paths to accommodating them is a really clear understanding of the contingencies, the corner cases, and off-nominal conditions. We have many famous examples, but one of them is the bird strike and a miracle in Hudson River movie. I'm sure some of you have watched it. That is sort of one of those cases that we must be able to accommodate. What happens when unmanned aircraft is operating, there is a bird strike? What are the cascading events happen? What kind of technological solutions and procedures need to be in place to make sure we can accommodate those? What happens they have an emergency? What happens they have a low fuel situation, whether it's electric or whether it's regular fuel? Number of these situations must be taken into account as they impact the mixed equipage problem that I mentioned before, and they could interact with other traffic that is in there. Now, so the question then always comes is, yes, we all want to accommodate these. We want to accommodate them in a safe manner. We want to make sure that we will take into account the nominal and off-nominal conditions. We do simulations, we do tabletop exercises, we understand the requirements and so on and so forth. What is the best way to operationalize them in the airspace system? So one of the premise here is this minimum viable product construct with risk-based progression. So now here I'll give you examples from United States. You know, obviously there is a bigger payoff in going to urban areas and complex airspace systems and complex areas with cargo. But that may not be the first step you want to do. You know, you want to do crawl, walk, run, and then fly in these cities. So here are the examples where, for those who have gone to Grand Canyon, all the way down the Grand Canyon, there is a village called Sapaya Village. And right now, the cargo is carried there on mules. So it takes forever, and it's not very efficient, as you can see. It requires people walking with them and so on and so forth. So instead, you could be looking at the unmanned aircraft system, a drone of medium to large size that can go up and down and deliver that kind of equipment when the risk is very, very low. The other example to start with is Hawaii Islands. So, you know, I used to actually give example in Alaska, but a lot of people would say, well, I'd rather go to Hawaii, visit Hawaii than Alaska. So, but Alaska has also many use cases, by the way. Hawaii Islands are 40 to 70 miles away from each other, and you can actually, the risk is so low because it goes over the water. It would be a really good stepping stone. Another example is a lot of places mail is still delivered on by boat, particularly when there is rivers and lakes involved. There are thousands and thousands of examples like that all over the world, and we could start the operationalization of these vehicles of different sizes through these characterization and risk-based approach, and demonstrate that the safety and viability of these unmanned systems, and slowly increase its actually reach into a complex airspace over people and so on and so forth. So as I mentioned, we talk in terms of minimum viable product. So obviously the best way the advanced air mobility unmanned or advanced air mobility is likely to be economically viable is when you have M2N, which is people operating N vehicles. So usually that ratio is less than 1. So you want 12 operations or 10 operations, 10 aircraft operated by one person, and that increases the productivity of these operations. But getting there is a very hard problem. Right now, we are still doing remotely piloted. Then you can go into one-to-one, but remotely supervised, and then towards the end we can go to M2N. Now, this is very complex, particularly if you're carrying people. So current conditions are such that many companies were focused on advanced air mobility, electric vertical takeoff and landing, which they are still doing simplified piloted operations, but they would like to get to the remotely managed, unmanned, and so forth. But so that's one theme, one type of application or use case. The other is really just the different sizes of drones, small, medium, large size drones. Still, we have regulatory conditions allow us to do remotely piloted. We want to get to remotely piloted, to remotely managed pilot on the loop, and then the autonomous and remotely supervised with pilot on the loop, and then towards an M2N, which is autonomously supervised, including all kinds of contingency management, off-nominal conditions done through machine and to machine interactions. A human involvement is maybe still necessary in terms of setting up the goals and the constraints and so on and so forth. And that's where a lot of research needs to occur to figure out what is the right human autonomy teaming that needs to take into place to enable these operations. Here is one example of how to accommodate that through architecture that we built for unmanned aircraft system traffic management. Now, granted, we focused on 400 feet and below, but these are smaller drones. Basically, they create their trajectories, areas of operation, electronically connect into the system, what we call unmanned aircraft system traffic management. The third-party services offer services such as trajectory planning, monitoring, and so on and so forth. And it's a federated system rather than a centralized system that allows operators to interact with each other through something called USS, Unmanned Aircraft System Support Service Supplier. If you really want to progress on the autonomy scale towards more and more increasingly unmanned or increasingly autonomous operations, we are of course going to build a lot of algorithms for perception and hazard avoidance and trajectory management. Then we need M2N. Then we need to integrate them on the vehicle itself. That has to be integrated into the awareness of the vehicle, as well as awareness of the outside conditions and better planning and contingencies, particularly in case of any external situations. Weather disruption is one of the big ones. GPS degraded condition is another one. We talked about bird strikes and so on and so forth. So integrating them into the aircraft, and then interoperability across many platforms in the same airspace. So whether it's electric vertical takeoff landing, different types of drone, manned supersonic, all the picture that I showed before. So it's a progression that we had to continue to maintain and demonstrate that the entire operations will be safer while as we continue to introduce new type of vehicles in the airspace system. In summary, I would like to suggest that we have a systems view, that we look at the entire gamut of operations and figure out how to accommodate them. Otherwise, it becomes a very complex problem. And it also, you had to wait. I mean, we had to make sure that the whole airspace system is ready when the aircraft are ready. You can imagine contingencies such as
Parimal, can you hear me? Your audio is gone. Ah.
thinking and identify procedures and technology and information.
Sorry for interrupting you, Parimal, but your audio was gone for 1 minute. So maybe you could start over again with the summary slide. I'm sorry, but we couldn't hear you.
Oh, yeah, I apologize. Sorry about that. My main point in the summary is that we need to have systems thinking. As I mentioned, as I showed, that we have individual autonomous aircraft, but they had to reside in presence of other aircraft. So it requires a systems thinking that we must have entire airspace system ready when these vehicles are ready and certificated. We need to take different scenarios, particularly off-nominal conditions, weather avoidance, weather disturbance, GPS degradation, as well as bird strike and inherently problems associated with low fuel and such, drive them through the entire end-to-end gamut in terms of tabletop exercise or procedures or simulations, as well as this field test. And then we need to do risk-based implementation. You build a little, you test a little, you deploy a little, and all of that would be supported by digital twins. So the more twinning we have, I heard the previous speaker was also mentioning something related to the twin. The twins we have, the better we will be able to do what-if analysis, real time as well as prognostics, and to figure out how to accommodate them and enhance the uses of unmanned systems. This is my last slide. Fundamentally, I want to leave with this message that we want to continue to innovate in the aviation with these new platforms, new use cases, new applications of unmanned systems of all sizes, and we want to embrace them, but at the same time, we want to maintain the safety tradition of the aviation. So thank you, and look forward to answering any questions.